We are recording. This is module 5, programmable logic controllers. All right. PLCs. There's some I'm kind of mixed on this chapter. Some of this stuff I feel like is good information. Some of it I don't. Either way, it's going to be on their quiz and stuff like that. Different trade terms that we're going to talk about. Human machine interface. You'll hear the words HMI quite a bit. And that is like, what do y'all usually think of when you think of HMI? Y'all work with that at all? Like a lot of times it's a control screen that you can like push and you can see different levels on different tanks and stuff like that. They say that's your human machine interface. The book uses that. Not only does it do that type of human machine interface, but also like any type of control panel with lights on. Like even if it has like a red and green light, start and stop, that they're considering that human machine interface. Just the buttons you're pushing to make stuff happen. Input, output. There's going to be inputs and outputs on all the different types of PLCs. So you can have mainly the two main different types of inputs and outputs are digital and analog, right? So a digital, what would be a digital input?
1, 0. 1, 0.
Ones and zeros. What's a device that is only ones and zeros?
On and off switch.
A switch. Like if this lighting in this room are on a PLC, that switch would be an input that would go like this is the back panel to the big motor control. So I have digital inputs 00 through 07. So I can have an input like a digital input right here saying input 1 is on or off, and that's a light switch. And then it talks to the brain of this and then configure an output, which we're getting at. The outputs are you can have, so you can also have an analog input. So that would be like your level transmitter on your tank over here. That is a modulating input. So 4 to 20 milliamps going into your controller. That's an analog input. Same thing for outputs. Analog output would be like an I to P. You're inputting a 4 to 20 and the pressure's coming out. That 4 to 20 coming out would be what's coming out of the PLC, like analog output. Digital output would be turning a light on or off. Right? So you want to have highlighted the I/O, the inputs and outputs. Modules we'll talk about. I can't ever remember what USB stands for, so highlight that one. But my first highlight in the reading is in 110, typical PLC systems, first sentence. A programmable logic controller is a microprocessor control device similar to a computer that can be programmed by a user to perform specific tasks. All right, so all like you guys have been learning how to do like a lot of that ladder logic and put all these circuits together using that ladder logic, right? So these PLCs have brains and the programming can be done in ladder logic. Your inputs or your push button, your outputs are your like valve controller or lights. Next sentence is highlighted. Unlike an ordinary personalized computer, however, the PLC is ruggedized and suitable for industrial setting. So I wouldn't say, like they say that, but any PLC I've ever worked on is in an air-conditioned room like this. Like it's in the control. It's where you want to work, right? So like doing PLC work, like I'd say instrumentation work, and then like PLC work is even above that. You get to like hang out with a guy that knows a lot about PLC. It's like that's what we're gonna learn from him because that's how you can stay inside AC and stuff like that. Top right of page 1, first paragraph up there, first sentence. The term architecture is usually associated with building designs, but in PLC it refers to how the whole system is put together.
Can I get a pen? Can I get one of those pens and like underline?
Yeah, that's fine. Line those, transfer them to your book and just give me that in a second. Skip a sentence and the last sentence of that, right before the bullet points is highlighted. The following are a few of the things that they considered when designing and building a PLC-based control system. I have the last bullet point highlighted, the types of human machine interface used to interact with operators. Examples of PLC systems. 111. I have in the reading, like figure 1 shows a micro PLC. I like that. I think it's the third sentence. And then the last sentence that goes along with it. PLCs of this type are common in situations where some intelligence is required, but large amounts of I/O is not. So that's the last thing that's on page 1. So that's what is one of my goals for y'all to do on the motor trainer is to do the lab on this. So this is where you only need, like, if you had a system that didn't need a lot of stuff. Instead of having like contactors and stuff like that working everything, you could have one of these micro PLCs and have just as little as 8 inputs and 4 outputs, and that's all you need for the system. And these are cheap, right? Whereas like the next thing it's going to talk about is these, where you can have several thousand inputs and outputs on like a big PLC, which is what you need, like a big plan or something like that. So there's a large variety from like, you know what a lift station is around here, the moving shit around the parish and stuff like that. Those have micro PLCs. Like I've opened up one of the cabinets before, like those have micro PLCs that they don't have to have a computer attached to. They just put the program in there and it works to do like, has floats and stuff on it. So digital inputs, like stuff fills up, it turns a pump on, it goes down, it turns the pump off, instead of having contactors that fade. Right? So they would use something like this for a small system like that. Whereas like PDF would use something like this for all the systems that they have, right? So good for small systems. Flipping over to page 2, first 2 sentences on page 2 are highlighted really with the rest of the paragraph. A typical medium capacity PLC is shown in figure 2. The particular system is rack mounted and can be expanded with up to several thousand I/O connections of various types. So that's an old picture. That's called a Slick 500. Like there's different brands. I think that's what this is going to talk about. Is like there's a lot of different brands of PLC. They do a good job of like showing different brands, but all this stuff is Allen Bradley, which is like what I learned on in college, and then I didn't see it again. Even though it's like an industry standard, there's different brands and they're fairly different from each other. So I learned Allen Bradley in college, and then I went to the steel mill and it was all Siemens, and I actually liked it a little bit better. But this is what it's showing, like medium capacity PLC. This is called a Slick 500, and it's old. Like this is called a Slick 5000. It's what I have up here, and it was like new whenever I was in college 15 years ago. So it's still like the industry standard and stuff like that, just because it hasn't, like you can put hundreds of thousands of inputs and that, like it's enough for whatever you want to do with it, right? And like you can have like this system here, and then one of these cards has an Ethernet cord attached, and it goes a football field away, attached to another rack, and they're all just daisy chained together and just doing different stuff out in the field, out in whatever you're manipulating and changing. But just a few, like we got 8 and 4 thousands. And then I highlighted the rest of the paragraph because it talks about like this one, and just how you can have like crazy expansions and stuff like that based on what you need. Next paragraph, I highlighted the entire thing. I know this is a lot of highlights, but it's where to highlight that. Figure 4. So thing down at the bottom or up on the board shows two examples of HMIs. One is very large and sophisticated. One is very simple. This key in on this next sentence. Buttons, switches, and lights wired on a panel or control box can function as HMIs as well. Each HMI must be tailored for the specific application. They must also be designed with ordinary operators in mind rather than experienced technicians and programmers. A good HMI requires very little instruction to be used efficiently. So these are both HMIs up on the board, as well as like just a push button station. So like how these work, like I've had a little bit of training and stuff on HMIs, and the way they work with a PLC. Like if you can see that tank up at the top, you can see a level on that side. That level is just a communication, like that is an animation that you pull from the program that you put right there. And then you would pull from the analog input for the detector on that tank and link it to that image. Right? Does that kind of make sense?
Yeah.
So you would have an analog image connected to an analog input on your PLC that's connected to it might be a differential pressure transmitter that's on the side of the tank, right? And then you link it to this. And then you can say, like, this is like some type of mixing thing. Well, all that is a normally open contact, normally would be a normally open contact on a contactor for a motor. Well, you have an input that says my motor is on going to my PLC, and you tie that address to this, and it turns on an animation, say, and a light or something like that, says it's spinning. And you just have a lot of these stock. I think you can go create your own. I never got to that point where I could create my own, but you just create these screens that kind of make sense for like these different plants. Like you have tanks and you have whatever, like scales and stuff like that. And you link them all in the programming back to what's going to this. Kind of makes sense. That's the smart version. And then like this would be an HMI just because it's telling you pressure and level. This is telling you one thing, where that thing is telling you probably about 100 things, right? Whereas a screen or just a panel with two lights on it might just tell you whether the motor's on. Anything that's communicating between you and the machine. Guess what? The next paragraph's highlighted. 120, hardwired systems versus PLC systems. So I'm gonna give you the highlights and talk about it. The whole paragraph's highlighted. First sentence is one highlight, the rest is another. The primary hardwired components of PLC are the power supply, the processor, I/O modules, and the communication modules. A personal computer is often used to program the processor, but this is not considered a primary component because once the processor is programmed, the computer is disconnected. This is one of those highlights that I don't like. That who cares? What's considered primary? Like, see this connection on the front? You connect to that with the computer, and once you disconnect, it's no longer part. Like hardware means like this stuff, right? That means that the computer's no longer attached to it, and it's not part of the system.
Yeah, that's how you install a program.
Right. It's not part of like the hardware of this. They're gonna ask you like a test question. I think that's stuff, but whatever. Also, like like it says, primary hardwired component. Like it's talking about the different. Yeah, it's just this or that. When it says modules, I've talked about this before, but it's like each one of these different things. And then this rack has a back plane. This is the power supply. Then it would have like a processor and stuff like that. That's the actual hardware of the PLC. 122. PLC controlled circuit.
Whole thing.
No, second sentence to the end. Just about the whole thing. As you can see, the switches are not connected directly to lamps. Instead, they're connected to an input module. The rest of it is a separate highlight. The lamps are connected to an output module. The input modules and the output modules do not communicate with each other directly. Just each is controlled by the processor. All that's saying is everybody has wired up this circuit over on the motor trainer, right? This is like number one circuit. This is hardwired stuff. This is being controlled directly. This is our power coming in. It's trying to get over there. I push that's a push button, not a switch. I push that, the lamp comes on, and it's directly connected, right? This is directly connected to this. All this is saying is that my light that's connected to my PLC, switch that on. I'm not turning the light on. I'm telling the PLC that switch is turned on. Like that switch is dumb to the fact that it turns on a light. Does that make sense?
Mm-hmm.
Like it's a light switch, but it's just a switch. All it is a switch, right? So it tells the processor, the brain, hey, this switch connected to this is turned on. So do this, turn on lamp one, or do flash lamp one back and forth, lamp one, lamp two back and forth 10 times in 30 seconds. Like that's the thing, like where you would have to use contactors and timers and stuff like that to get these lights to do something goofy. Whereas somebody can program that in about 30 seconds, and it's stoplight, right?
That sounds way easier.
Right. Way more cost effective. I've shown you all the different stuff that can go bad on contactors and stuff like that. Like stuff goes bad. They last for a long time, but they go bad.
So I got a question.
Yeah.
So I was on an LNG barge yesterday. And the way they have it set up, they got these cryogenic valves, ball valves. They got the actuator on it, and they got an indicator that sends back feedback of whether it's open or closed. They got a line that comes through a regulator, through a solenoid valve, through two needle valves, into the actuator to give the air to open.
Mm-hmm.
And it's a spring return actuator, meaning when you take air off, it's going to shut, it's going to close. So when I was troubleshooting it and I told him to send it a signal to open, I took the hose off the solenoid valve to see how much air was coming out. It popped open, air came out, and then after a couple seconds it stopped. Shouldn't be doing that, right? It should stay open.
Solenoid valve.
Yeah, solenoid valve should stay open. Could that be an
Is
issue?
it into PLC?
What do you mean?
Like, is that solenoid controlled by PLC?
Yeah.
There could be, if there's a pressure sensor somewhere else, there could be programming that says like, shut this off if this isn't done. I mean, like, who knows?
Yeah.
If this isn't getting a signal, shut this back off. Like you're saying, it should have stayed open. The thing I would have done was check this. I would have grabbed my voltage detector and touched that solenoid and saw if it was getting voltage.
Mm-hmm.
And if it was, then it was getting a signal to stay open or whatever, vice versa, whatever was supposed to open. Does that get a signal or not? And then inside of was somebody forcing this from a PLC?
They're giving it an open command. It's basically an open command, but it's sending the solenoid voltage to open.
So what I would have done is there's a way to search in the programming, like go see what he's forcing open and close, and you take that bit and you can search everywhere that bit is used in the program and see what's either telling it not to be turned on or like going over. Kind of the way it works is like if it's written before, it will override that function, and you can go see whether it's being told to turn on or off. So do I have a signal? Does my solenoid feel hot? Is it getting power? That's the first thing I would have done.
Mm-hmm.
And if it's not, you got to go see why it's not. Why is him forcing it on or off, however he's doing it, being written to that output and the output not firing? Because something's being written on top of it.
I know the solenoid is working because you hear it pop open, and I felt the air come through because I took the hose off to feel it, make sure we had good air pressure because half the gauges weren't working, and all of a sudden it pop again
and it goes close.
And yeah,
to me that seems like something in the PLC is telling me to shut.
Yeah, that's what I was figuring.
So there's the only way I would know is to take that bit, that's a digital output, and go see, like you can plug it in, and it should pull up a list of everything that controls it.
So do you think it might be because that solenoid and the indicator are separate? They're wired in separate, they're brought back in separate. You think maybe there's something where if that indicator doesn't show that it opens after a period of time, it shuts off the solenoid?
Yes. Yeah, that's probably what it is.
What it is.
Yeah.
That makes sense.
Yep. That would be my guess without looking at it. Not connected directly, lamps are kicked. I gave you all the rest of it there, right? Lamps are connected to an output module, output modules do not communicate. All right. Comparison of hardwired and PLC systems. Last paragraph on the page, last two sentences were highlighted. Many PLC inputs use devices called optic couplers to separate the inputs from the processor. These devices can protect the processor from voltages up to several hundred or even thousands of volts. So some knucklehead is running PLC input wire next to power wire that they didn't follow like what you're supposed to be doing, and it shorts together. They're just saying that they have things that can protect these because these are $5,000 to $7,000 a piece, right? And you don't want this getting to the backplane of something that is hundreds of thousands of dollars. Opticouplers protect your PLCs. This goes through the advantage and disadvantage of like kind of what we were talking about. Advantage of PLCs versus hardwired stuff. You guys have done a lot of hardwiring. All the like think about when you started with just like a push button going to a light, going to like a reversing contactor station, right? Just a rat nest of stuff. You take that rat nest of stuff and you're just putting into here, and you can make all that stuff do whatever you want. I have the third paragraph on page 4 highlighted. The advantage of a PLC becomes evident when circuit changes are required. For example, in order to change the circuit of a hardwired system to have switch 1 control lamp 2 and switch 2 control lamp 1, it would take several minutes to rewire them and would involve moving wires. With a PLC, a simple program edit makes this change without rewiring needed. In my experience, I didn't do a lot of like PLC programming. I wasn't going and getting devices and getting the inputs and outputs and stuff like that. I was a I did troubleshooting. So PLC's troubleshooting was amazing because I could look at, instead of walking all the heck over the steel mill, 3,000-degree ovens, looking at gauges on the side and stuff like that, I could sit in a room like this and look at the computer screen and look at I could pull up HMIs that the operators had and stuff like that, but I could go see more than that and look at the actual inputs and outputs and stuff like that, scrolling through a computer and see like, that looks jacked up. Like that input is like either missing or something like that. And I can't remember, like stuff would show you faults. Like if something like say 4 to 20 milliamp wiring got crushed somewhere, like, I think it would show stuff like that, but it would be very easy to see because like scrolling through this, like this usually would say on or off, and it would just be like all question marks or X's. Like, and it was a great troubleshooting tool. Rather than if you're doing that, like think about a reversing contactor station, you're out there with a meter checking every single coil, seeing if that coil is being called to be turned on and stuff like that. Answer those 5 questions on page 6. I'm gonna run through these. Number one, PLC interacts with the outside world through its
IO mod.
I/O modules. That's how stuff talks to the PLC and PLC talks to stuff. Two, how does a PLC differ from an ordinary general purpose computer?
Organized.
Organized, whatever that means. Three, biggest difference between a large PLC and a micro PLC is
IO connections.
I/O connections. C. Four, PLC directly interacts with their operators through
Mod.
HMI. What does HMI stand for?
Human machine interaction interface.
Interface. Five, a hardwired system controls the outputs directly with its inputs. How does PLC use its inputs to control its outputs? Processor, which is the brain. Questions on any of that stuff? This next part, like, will be a little bit of I feel like we step back a little bit just because we've jumped around so much this chapter. I guess the trade terms motion encoder is something that I actually use in the field and stuff. Anybody ever mess with an encoder? Usually you just hook it on to something that spins and it can give you like a linear function for how many times something is rotated. We used it a lot on, we had the big overhead cranes and stuff like that. And that's what said like how far up and down the block was and stuff like that. The encoders for quite a bit. It's just it's an analog device that has to have a special function to go into PLC. Binary numbers. This is the highlight is the sentence right in between the like 10 to the third to the 7th. With binary, each column is added to the left is an increasing power of 2. So you need to know like the kind of what we showed before. Like this is the ones column, twos column. Am I doing that right? That's the 2 to the 0 would be 1. Because there's 2 digits, anything to the 0 power is 1. So that's the ones columns, 2s, 4, 8, 16, 32, 64. Everybody feel comfortable with doing binary to decimal conversions? If I said, how would I do the number? Most of the time you're going to do 4-bit binary. 4 bits of binary is called a what? Byte. Nope. Word. So if I wanted to say the decimal number 12 for 4-bit binary, how would I do it if this was the ones column, 2s, 4, 8? How do I get 12?
1, 1, 0, 3.
You would do 1, which would take 8 out of it. So minus 8, which would leave me with 4. I have 4s. That would give me a 4. 0 left. No 2 or no. 0, 0. Does that make sense? Do I need to do another one? Let's go with that. You'll have some practice in the quizzes and stuff like that if you need to do that more.
Which still, like on the board, they got the 53 and they got the little number.
That's just saying it's base 10, which is decimal. That's what we use as decimals. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then that's the carry to the next one. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, carry to the next one, base 10. It goes up in tens. Rather than this, shows a 2 at the 1, 1, 0, 1, 0, 1 is 2. It goes 1, or it goes 0, 1, back to 0. It only has 2, but it can go in between where 10 has 10. That makes sense. Binary to decimal conversion, second paragraph is highlighted. This is kind of what we just did, but this is the steps to do it. Converting from binary to decimal is fairly simple. If a 1 is present in the given position, the column value for that position is added to the remaining sum. If the 0 is present, ignore that column and move on to the next position. In other words, define the decimal equivalent of a binary number, multiply each digit by its place value's corresponding power of 2, and find the sum of the results. For example, to convert binary number 101101 to its decimal equivalent using the following process. Like you can go through and use their process if you want, or I like my process better than their process. So if they're saying 101101 base 2, so that tells you it's binary. So I just go through, like binary is always, it's a left to right or right to left.
Up to right. Right to left.
Right to left. So we start over here, and I know this is my what column? Ones,
2, 4, 8,
8,
16.
32. So, and then if it's turned on, then I get that number. So do I get a 1? Yep.
Yes.
So I get a 2?
Nope.
Nope. I get a 4, I get an 8, and I get a 32, and I add them together. 40, 44, 45. Is that what they got? 45. And that's a decimal number, so that's base 10. However you want to do it, right?
So is it always gonna be base 10?
Base 10 is just saying that it's
Decimal.
decimal. That's all. We say, like, we write the number 67, and we assume that it's decimal. But if we're talking to a computer, we have to tell it that it's decimal or something like that. Like you have to, like, it doesn't know, we just assume because that's what we use. Decimal to binary conversion, all I'm gonna do is tell you to highlight the steps. Like, y'all can go through and do, like, it's just the opposite of that. But the steps to do that are steps 1 through 5. Highlight those. You're gonna have a couple of questions based on that. Hexadecimal numbers, this is why I think we didn't do as well on hexadecimal, because I didn't go in order. So 220. Hexadecimal numbers. First sentence on page 9 is highlighted. Hexadecimal, which is base 16. So we've done binary, which is base 2, decimal, which is base 10, hexadecimal is base 16. Uses 16 digits 0 to 9 and A through F to represent numbers. So you can go through, I have all of 2 to 1 highlighted. The hexadecimal binary conversions. You can go through theirs, or I'm gonna go through how I do it. And the reason we're going through this is because these PLCs can talk in different languages with different amounts of bits and stuff like that. Yes, everything boils down to binary, but different special modules that have encoders might be kind of talking in hexadecimal, because you can do a lot more data in hexadecimal. Like saying like their first hexadecimal number is A6E2. Well, that's what I'm converting binary from to another. Like, it's just, you have to know the rules in which you're talking to what component that you're talking to, if that makes sense. Yes, light switches are easy. It's either on and off. That's easy with binary. But if I have something that's sophisticated, it's going to take more than just on and off.
So that's how they kind of make like words on the screen. They
Yes.
just have some way
Yeah.
to put this amount of numbers equals A.
Correct. That's how we do that's how this screen is on the board right now. Like, is that data? I don't know what this is talking with, but something all the way down to that binary logic is telling each one of those little digits to be on or off. And it's not just talking in binary, it's talking in probably hexadecimal or something more. So highlight all of that. The thing that hexadecimal is going to be base 16. So 0 through 9 are just as they are. They're 0 through 9, and then 10 through what is that? 16? Or is it 15? No, 16. 10 through 16 are letters A through F. So like A is 10. Oh, because we have 0. 0 through 9 is 10 numbers, right? So then we go to 15, which is 16 numbers.
So is that universal or is that just for what we're doing now?
What? This is hexadecimal. Like universal, like this is how a hexadecimal is. I think they have the advantage of like the United States designed this stuff, so they get to use the letters they want. Like, okay, I can say that. I have no idea. That's being honest. I've never done anything in China. They might have something crazy different, but like, you might see that more being on boats and stuff like that. I've never seen hexadecimal. When I do PLCs, there's a drop down list of how you want stuff to talk to each other, right? And it's like an array. It's coming up like it's an
Yeah,
array.
I watched something on the other day. It just looks like you're writing out an electrical diagram.
Right. Like you pick how you want this thing to talk to your PLC, and that's the furthest that I've ever gotten in my career to get into that. This is how it's doing at the base level. And even going below this is like the digital logic stuff that we talked about in the last chapter. Going below that, that's like turning those into like dials. So way more sophisticated than I could ever think of to create this stuff. But this is like at the base level how they communicate. You have to set rules forth on how you talk to each other. So your device and your thing have to be talking in hexadecimal or digital or binary. And this is just one of the most efficient ways to talk because it can store so much freaking data. All right, that's about as far as I can take it. Like if you want to go further than that, have at it. But 221, read through that, and they'll talk about how to change from one to the other. I'll go through like to me, I go to decimal before I go straight from hexadecimal to binary, or from binary to hexadecimal. So looking at, is this the number that's on the board? 6AE2. I'll do the one that they have. 1010 0 0110 0 0010. All right. So I just use my numbers over here to figure out what decimal it is, and then I go to hexadecimal from that. So do I have any ones? Nope, but I've got a 2 and a what?
8.
8. What number is this?
10.
10. What number is that in hex? Is an A. So decimal, hex, binary. If you can go straight from binary to hexadecimal, good for you. This is easier for me. No ones. I've got a 2 and I've got a 4. This is 8. 8 in hex is 8. I've got not a 1. I've got a 2, a 4, and an 8. 14. 14 over here. If A is 10 or 14 is E, all I got's a 2. So this is a 2. 2 is 2.
And 4 and 2, 6.
Oh, wait.
On the second? Yeah.
Oh, you're right.
8.
You're right.
Not that one, no. The 8.
Oh, 4 and 2 is, yep.
Uh,
6. 6 is 6. This was right, wasn't it?
yeah.
14. 14 is E. And that's 2, right? A, 6, E2. Is that what they did?
Yeah.
Okay. Does that work? Does that kind of make sense?
Yeah, where'd they get the decimal 16?
It's
Because it's hexadecimal, and I have 0 through 9, which is 10.
Oh,
And then I have a little bit more to play with. So I have 16 bits of information to play with. Hex is 16. 231. I've got the first paragraph and most of the second paragraph highlighted. Like you can just highlight all of it. I'm going to talk about the first paragraph first, and then the second paragraph is split up into 2 highlights. One of the most useful ways to enhance human computer communication is to be able to work with letters, numbers, and symbols. In other words, text. While computers internally handle all information as binary numbers, HMI devices can work with text. For this reason, schemes that represent text as binary numbers were developed in the early days of computers. One of the oldest and still most commonly used is, I've always called it INST. So this is the device that will turn whatever I'm typing in my computer, will turn it all the way down into binary information. All right. We can see how that's useful because, like, you've heard of coding and stuff before. Anybody know the function to see the code? So you've heard of like programming like C++ and Python and stuff like that. That's using symbols such as like what we type in our computer and stuff like that. It's so stinking slow. To turn that into programming, which gets all the way down to binary, right? We can see why that's useful because it's like a different language that can be turned into whatever talks to the computer. There it is. So I don't know if y'all have ever accidentally hit Control U on a keyboard, but like you hit that and this is how the website was written, right? Somebody's out there that can read that. Not me. That's not ANSI, but it's something, I don't know what code it is, but that's the beginning of that was ANSI. Okay? So that writing that out and doing all those like functions and like, I mean, you can kind of read this stuff. Like this is like I did very little of this in college, like to where these functions, but like JavaScript, everybody has heard of JavaScript. Well, a question mark, exclamation point, JavaScript, colon means do something specific, talking to a computer by telling it to turn on different bits and stuff like that. That might be like turning this color on this part of the screen. Like that's how they get all this stuff. So ANSI was the beginning of that. Next paragraph. ANSI stands for American Standard Code for Information Exchange. It is 7 or 8-bit binary code with each number represents a standard character of some kind. Early ANSI systems use 7 bits, going a total of 128 possible characters. Not all of these corresponded to visible characters. Instead, some acted as control code that modified the behavior of certain types of devices. Skip a sentence. And I've got that second to last sentence highlighted. Many computer manufacturers later added an 8th bit to the ANSI standard, which made an additional 128 characters available. They needed to process more data. They needed another character, right? So that's how this stuff started, where you got from like that stuff, whatever was on the board, into like doing actual things. Flipping over to page 11. Binary coded decimal. So we did that. That's where we used like 4-bit binary to make one number. So BCD, like I could have a number. Or 6,432. I can turn that in any numbers 0 through 9, I can turn into BCD code. So, like a 6 would be equivalent to what in decimal? 4-bit decimal. Is 6 going to be, the first one is 0, 1, 1, 0, right? A 4 would be 0, 1, 0, 0, 3, 0, 0, 1, 1. 0, 0, 1, 0. So that's BCD. This is turning into that. That's binary coded decimal. This is coded decimal. My highlights for that are in the first paragraph, second and third sentences are highlighted. To convert a number from decimal to BCD, each decimal digit is simply turned into its equivalent 4-bit binary number. To convert a BCD number back to decimal, it must be broken up into 4-bit groups. The last two sentences are the example. For example, the decimal number 127 What does that 10 mean? Decimal, base 10 equals the BCD number 0001001001111 BCD. BCD obviously means that it's a BCD number. Similarly, the BCD number that equals the decimal number 9876 base 10. Is everybody good with going back and forth between that stuff? BCD numbers. You'll have a little bit more practice doing this, but you're basically, and they will put all this together. They won't break it down for you. Whatever number they have, it will be a multiple of 4. So you could have a BCD number of 2 numbers, which would just be 8. But you could have, this is 12, you could have 16, whatever. It's not going to be an odd number of numbers, right? But they just pack them all together and say BCD at the end. You break them up into 4 bits and then create a decimal. Gray code 233. First sentence is highlighted. Gray code is a modified binary code used by rotational or linear motion encoders to convert motion positions to a digital value. So that's what I was talking about. That has to have like these encoders. They look like a little bitty motor. They have a lot of wires coming off of them. And the wires have little magnets on the inside, and that's what turns them on and off. And that's what you can create rotational code, which is gray code from an encoder. They're on stuff that goes, well, I say it's on stuff that goes up and down. So I'm used to using them on cranes. You can see like the big, everywhere around here uses cranes. Like when operators need to know like how far down or up something is, they can use encoders and stuff. But they use gray code in order to do that. Take a second to answer those 6 questions on page 12.
left your way in the forward.
What's that?
Maybe we're doing the
hexadecimal, like you had your way.
Yeah, I gotta go to the decimal before I go to the binary. I can't. I've read through how they've done it and tried to teach it.
yeah, so I'm looking at how
It's
they,
converted to decimals.
yeah, but seeing how they did it, and I was like, man, the way he did it over here.
It doesn't make sense to me the way they did it, so.
So it's hexadecimal if it has 16,
Yeah,
and it's only decimal if it has 10.
yeah.
Yeah, decimal, like, it's like a decagon has 10 sides. Hexadec, hex 6, des 10, 16. All right, I'm gonna run through these. You'll have more practice on the modular review quiz as well. Number one, what is the value or weight of the fourth column of a binary number? So, which one of those is the fourth column?
First one.
This one is my fourth column because I count right to left. 1, 2, 3, fourth column. This is the ones column, twos, fours, eights column. So the answer is B. Convert the number
Yeah, that's
0101, 0101, 1101, 101, base 2 binary number to decimal. All right, so we've got 1, 2, 3, 4, 5, 6, 7, 8 placeholders, right? All right. We put our, I'm gonna put my column, so 1, 2, 8. This is my ones, twos, 4, 8, 16, 32, 64,
28.
128.
Yeah, 128.
Yeah. Okay, so going through this in order, I'm gonna go from right to left just because that's how they do that. So I've got a 1.
One.
Not a 2, I've got a 4, I've got an 8. Ones, twos, fours, eights. I've got a 16 and a 64. Everybody with me so far?
okay, I got it.
4 plus.
64 plus 16 gives me 80, 88, 92, 93. This is decimal number, so it's base 10. One last thing on this one. What gave it away that it was C? Did anybody notice that?
They got the last one's a 1, so it makes it an odd number.
It is the only odd answer. So that is it has to be C. That makes sense. Like that is the only right answer, so it has to be 93. Convert the number 39 base 10 to binary. So 39. So I've got, these are all, so the way I do it, going from decimal to binary, I go to what my biggest number is here. So what's my biggest number that'll go into 39?
32.
32. So I subtract 32 and I get 7 left. 16 going to 7, nope, 8 then going to 7, 4 goes into 7, 4, and I've got 3 left. 2 goes into 3. I got 1 left. 1, don't have either of those. 0, 0, 1, 0, 0, 1, 1, 1, base 2. Should have been your answer. Questions on that one? That makes sense? Like just kind of setting it up and then subtracting until you got 0 left. You'll always have 0 left. If you don't, you did it wrong. Convert the number 7F to binary. So I can't go hex to binary or to binary. I've got to go from hex to decimal to binary. So they said 7F 16, I gotta go to decimal first. So 7 in hexadecimal is what in binary? 7. 0 through 9 is the same, right? And then F in hex, all I know is that 0 through 9 is 0 through 9, and A is 10, and it goes through F. So if I know A is 10, what is F? 15, right? But I have to go through my head. So this is 7 and 15, right? Now I convert this to binary.
So you convert in 715 to binary?
No, they're separate. This is going to be all binary.
Oh, but in like codes of 4 and
Because
4.
this is one, and then this is another.
So 4 and 4.
Yes.
Yeah.
So in order to get 7, what's my biggest number that'll go to 7? Nope, 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 nope. I got a 4, which will give me 4, 3 left, and then a 1 and 1 will give me 2 and 1. So my binary, 4-bit binary for that, is that what they're wanting?
0, 1.
0, 1, 1, 1.
Yeah.
Right? They don't add the rest of that because, well, hexadecimal doesn't use those numbers. It just uses 0 through 9 and then 15. So then we go to 15. What's our decimal number? Biggest number that we're going to 15 is 8. 15 minus 8 is 7. 4 going to 7. I'll have 3 left, and then I'll have 1. Is that 1, 1, 1, 1? There you go. Okay. Does that make sense? Number 5, characters that modify a device's behavior rather than representing text are known as control codes. D. Convert the number that to decimal. All right. Well, they're going to say. So the first thing you have to do is see how many numbers you've got. There's 8. There's 8 bits there. So I know I'm going to have a 2-bit decimal number. Okay. The first 4 is going to be the first number. Second 4 is going to be the second number. All right. So now I'm just using these. So my first BCD number is 0, 1, 1, 1. 0, 1, 1, 1. We just did that. That's a 7, right? 0, 1, 1, 1 is 7. So I'll have a 7, and then my second one is 0, 0, 1, 0. 0, 0, 1, 0 is what?
2.
Is 2. So I have 72 BCD. Everybody go with that? Or no, 10. We went from BCD up there. This is basic. This is basic. Sorry. The answer is A. 2. Section 3. PLC hardware. Address. So whenever I was saying like going through an HMI and you've got the analog thing that's going up and down, like that address is what's tied to like inputs and outputs. It's an address and it's specific, like it's kind of specific to the, like I talked about Allen Bradley and Siemens and GE all have different PLCs. That's where they get a little bit different is how they do addresses and stuff like that. but you just have a unique number that is tied to each of those things. That's what addresses is. You just have to tie that to it because it address, you need to know where it's going. Analog digital converter. We're going to talk about non-volatile memory versus volatile memory. A scan is important for a PLC. I don't remember the highlights of this one, but a scan, like where I talked, you asked that question. I said, like, if something happens first before something else, it's going to override it. Well, like your alarms and permissives and stuff like that are always written above other stuff so that they override them because they're more important. And scan, like in PLC, the scan happens like every 10 milliseconds or something like that. And like it goes through the ladder logic, like it reads it exactly how I tell you all the hardwire stuff, top to bottom, left to right. That's how a computer reads through the code. And it does that like multiple times a second. But if something's written before something else, that's where a scan is important because it reads top to bottom, left to right. Highlight 310, second paragraph, second sentence. For very small PLCs, the power supply is often internal. This PLC right here, it has an internal power supply. We went through all, like you've been through, you should have gone through a lot of electrical classes and stuff like that. Most of our stuff is in series circuits and stuff is paralleled off of that, like the lights and stuff, we all paralleled off. Well, with a PLC, older PLCs used to have to run to contactors to control more things. Now these power supplies will power like the lights and the pieces of instrumentation. Instrumentation has gotten better. It doesn't take as many volts to like get a differential pressure meter to come on. So it's not as much of a load on this. So they can the highlight was this has an internal power supply. This one has separate power supplies.
Where's it at?
It's the second paragraph at 310, right in the middle, second sentence. For very small PLCs, power supply is often internal. Last sentence on the page is highlighted. The voltages used by electronic devices found in most common control circuits are very small, often 5 volts DC or less. That's a lot of stuff is 5 volts that we use in the instrumentation world. The rest, actually, the next sentence, 2 sentences is highlighting. Static discharges from improper handling can destroy them. Static discharges are stray voltages from process equipment processes or non-process activities such as welding can destroy electronic devices as if they're not properly grounded or shielded. All of these PLCs, like this will have a ground, like this has to be tied to the ground. These, it's usually, like you can see where it was cut off, like the ground, these have to be grounded. You don't want, like I said, these modules are $5,000 a piece, new. You don't want to fry every single thing in this expensive stuff. It has to be like even static discharge is not good for this. Processor modules. So I've talked about them a lot, but this is the point where the book actually talks about it. Processor memory. That would be like this is just the power supply right here, but the processor looks kind of just like this, except it has like a USB port on it. But it's the brains of the PLC. And it has volatile memory and non-volatile memory. And what that means, let me give you the highlights and I'll talk about what it means. 321 processor memory, third sentence. The program itself usually resides in non-volatile memory so that it won't be lost if the power goes down. Separate highlight, volatile memory contains data and other temporary information that the PLC generates and uses as the control program runs.
Nothing in the process module was highlighted?
No. I mean, that's, the processor memory is part of the processor module, but
So what would be an example of something that would be volatile and something that would be non-volatile?
I'm showing you. Everybody's wired up that circuit, right? Just a regular start stop. What is this called? Latch. A latch or a seal, right? So I would write this into the PLC, and this would be part of the code, and this would be part of the non-volatile memory. That means if the power got shut off and I turned this back on, this would still come up, right? Volatile memory is, say this was running. So these are digital analog inputs. Digital, because they can just be, it's a push button is either on or off. So say this system is running and I have pushed my start push button, my CR1 came on, one CR sealed this in, power goes off. This being on is in volatile memory. It doesn't need to save that back to the processor to always remember that this was on the moment the thing turned off. That data is in volatile memory, and when power comes back on, this will be like that. Does that make sense? So volatile memory is like temporary information that is not stored for forever, right? The program is kept in volatile memory or non-volatile memory, and then how the program is working is kept in volatile memory.
So like a valve or a pump would be non-volatile, meaning it knows it's there, whether it's on or off, would be volatile.
Right. In the moment.
Yeah.
However it is normally supposed to be is how, like when the power comes back on, that power will be. It's like turning it on for the first time. But how it is the moment power goes off, that's the volatile memory. But it's still data that is still communicated. Like this is still ones and zeros that are held in place while this is running. It's just wiped out with power shut off. Last paragraph on, or first two sentences of the last paragraph on 14 are highlighted. The PLC's memory is organized into various areas depending on how the processor uses the data. This organizational diagram of memory is called a memory map. These are ones where like these highlights are just kind of more fact highlights, not a lot to talk about. Page 15. The third paragraph, the little bitty paragraph on the left is highlighted. All data is stored in what's called the data table. The data table is divided into 4 areas: the input, output, internal storage bits, and storage registers.
This is it?
This is on page 15, third paragraph. Starts with all data is stored. So these data tables, like that's where that's like the matrix stuff, like the background of the matrix where it's all ones and zeros. That's what that is in the PLC. All those ones and zeros, all the stuff that is written to control this 1 and 0 and this 1 and 0 and this 1 and 0. That's where all the stuff is kept. Last paragraph in the bottom left. First sentence is highlighted. Storage registers hold larger chunks of information, which are words. So again, words are just 4 bits of information. Processor scans, I got the beginning of the paragraph through the word scan highlighted, 322. The processor module controls the system by executing the control program. During program execution, the processor reads all the inputs, evaluates and acts upon them according to the program logic, and then modifies any outputs affected. This process of reading inputs, executing the program, and updating the outputs is known as a scan. So I kind of read that wrong, like I kind of told you that wrong. I said it did top to bottom, left to right, but really it does all the inputs, like what push buttons are pressed, who's pressing what in an HMI, what's happening, what level controller is doing in here. sends that to the brain, and then outputs goes on that, and that's a constant scheme that's happening. And that sounds like me going through it. The PLC did that 1,000 times, me just saying how it worked, right?
So,
It does this instantly almost.
so is hacking just changing this up in a computer?
I don't really know. I mean, it can. There's a really interesting to me documentary, like where Iran was using PLCs to control their nuclear stations, and like people hacked into that. And if you can imagine, I don't know if you know how nuclear works, but like you move control rods in or out, and like you can create a bomb. Like, can you imagine somebody getting a hold? Like, this is just
Just blowing up.
this is just a computer. Yeah, I don't remember what happened at the end of that, but hacking, I think, would just be like getting control of that. So normally you would download a program into this and then disconnect, right? And then that's the advantage of, so that's PLC. Download the program. PLC is no longer a part of the hardware, and it is its own system. So it's not really going to get hacked. Whereas like a
So it's like a virus, basically.
yes, like a distributed control system, it's the whole plant that's still connected to the computer. So I would think that would have a more likely chance of getting hacked than a PLC.
So is a computer virus just like a program you put in that just destroys and messes up
I think it's
what it's
like,
got in there?
computer viruses can be all different types of things. Like, it depends on what you want and what you want it to do, whether you want it to destroy or block access or whatever. Like, and a virus can be a virus can be somebody writing bad code. Like somebody literally writing this. It, like, your problem could be bad code, could be a virus, like something not working the way it's supposed to. It's probably not. It's probably a safety thing. But I've definitely had, like, they let me write code, and I was a 22-year-old out of college into like many multi-million. Like, I could have messed something up, right? I could have put a virus. A virus is anything that's wrong. So a hacker would be somebody that's using that to their advantage to gain and figuring out a way to gain on that. Whether taking, like, you can't control it anymore and give me money to control it, or mess somebody up. And page 16, IO and communication modules. So I've talked about IO modules quite a bit. Like just the different modules inside of this. So you can have the discrete numerical data, analog. Special would be like a RTD or a thermocouple specific module. Discrete modules 332. My highlight is on the right-hand side of the page. Second paragraph, last sentence. The power and logic portions of the interface device are electronically isolated from the processor to prevent damage and noise and power surges. So I think that's kind of self-explanatory. There's something in between the digital inputs and outputs to separate it from the brains of the operation. Numerical data interface modules. The highlight that I have is the second paragraph, first sentence. Like, really, you need to read through those two paragraphs. What that is, these are interface modules for like encoders, right? Like stuff that's going to have large bits of information that's going to be coming probably in hexadecimal. It's not going to be discrete information that's just ones and zeros. These numerical data information models, like, these are large words or large bits of information that is coming super fast. It's not somebody pushing a push button. It's something spinning or something that's creating a large amount of code all at once. The second paragraph, first sentence is what I've highlighted. Numerical data I/O interfaces provide connections to multi-bit digital devices. So like a multi-bit digital device could be like, we talked about a 7-segment display. that uses multiple bits, whether to just turn on all of these different things. That's a very simple device, but it's using each one of these is a 4-bit binary word. So that's a lot of information at once. So you need something special to talk to something that's talking to that. Analog modules, highlight fourth paragraph, first sentence. An analog output module receives numerical data from the processor, which converts it into an equivalent voltage or current signal with a digital to analog converter. So, brains, like something saying a level transmitter is saying the tank is too low. The processor says send a whatever milliamp signal to the control valve to open up or close and fix this problem, right? But they changed that. They changed the digital to analog, like in the brains of the computer are ones and zeros, but it changes it to 20 milliamp signal. That's all that's saying. That's a digital to analog converter. Special modules, whole paragraphs highlighted. While discrete numerical and analog modules handle the majority of PLC interfacing needs, there are occasions when specialized devices may need to be connected. Might have been wrong on the. I don't know. Examples include high-speed encoder counters, servo controls, stepper motor controls, synchronized access controls, velocity control, temperature monitoring controls, and smart transmitters. I guess the encoders aren't part of the numerical interface modules. Read back through there, but it's just a multi-bit thing. Flipping over to page 18, if you go to I have the whole temperature monitoring controls highlighted. You need to note that like the temperature monitoring controls is a special module, and the thing to key in on is the sentence right after couple sentences right after where you see ADC. In the bottom left. The numerical values for each input are processed by an internal microprocessor as an input to a PID loop. The processor executes a PID algorithm on each input. So module 10 of your, I don't know how y'all did on module 10 last semester, but it talked about like you guys did PID controlling and stuff over here, but like the math that actually does that stuff like is done in the special modules with thermocouples attached to them. Communications module. I got one of them right here. It's just an Ethernet module. 336 on page 19, 1, 2, third paragraph where you see Ethernet through the end of the paragraph. Ethernet and Wi-Fi are currently the most common networking technologies providing wired and wireless communications, respectively. Many PLC processors have a built-in Ethernet port. That's right up from the front, like that's how these are talking to each other. So they can talk. I mean, the digital, like y'all made up Ethernet cords. There's 8 wires in it. Like that's how it's sending information back and forth to each other. Still impressive. Top right of page 19, the sentence that has serial network highlighted. Many PLCs also communicate over a serial network, such as RS-232, RS-422, RS-485. That's old. There are still PLCs that use, y'all know what a serial cable looks like? Like it's like the old school computer cables. They did use these like whenever I was in college and stuff.
Like a VGA. What, this cable? Oh, serial low.
Oh.
These.
We'll still use those.
Yeah.
Yeah, they'll still use them and stuff like that, but these are being replaced by Ethernet cord.
Yeah, the newer systems I see on the boats, it's all Ethernet.
Yeah, it's all Ethernet stuff. I never saw Wi-Fi. Yeah, I never Wi-Fi doesn't seem like it's good. Like even though we've had Wi-Fi.
Now they are coming out with Bluetooth.
I could see Bluetooth because that but that
Kind of risky.
That's what I feel like.
Because like anybody can get into it. There's no lock on it. If you have Bluetooth and I can walk up to, like, I can go on a boat that's got Bluetooth limit switches for its valves. If I have the app, I can walk up to it and I can change its address and screw up your entire thing. It's crazy.
Nope.
Better not fire anybody on that boat.
Mission modules, serial network, like it's old stuff. It's just it's how this stuff. These are the rules and stuff of how this stuff is talking to each other. Nothing in module addressing. Take a minute and answer those 6 questions on page 1.
If I was a school doesn't have like a PLC for a class to take.
And they would never find anybody to teach it.
Why not?
My base salary is 52,000 a year.
And they wouldn't pay them enough?
Do you think you could talk somebody into how much you think a PLC guy makes?
I have no idea. I never looked into it.
I bet it's more than $52,000.
I can guarantee you that.
Yeah. So North Shore has a guy that's really good at it. But that dude is spread so thin. Like he's teaching another college too. Like he's like slam packed with stuff.
They teach PLC stuff in North Shore?
Mm-hmm. They really do. He's more of a I know he's more of a hands off, like go figure it out type person, but I'm pretty sure he's pretty intelligent with stuff.
Mm-hmm.
Yeah, I don't know how far he gets into it. I just know when they had the mechatronics program, I was teaching instrumentation and electrical. He was teaching robotics and PLCs. Yeah. The best PLC training I ever had was when they sent me to, like all of our PLCs were G. And they sent me to G class per week. And they had levels. Like I think I could do a couple trainings a year. Is that training $500 for the week?
How much?
I think it was like that was like 10 years ago. More than 10 years ago. Like $3,000 or $4,000. Most of these trainings are, but like they'd let me go, especially if I went on an off days, they'd let me go.
Where are they holding that? Like out of state?
That one was everything was out of state. I think that one was in Roanoke. Right. Question 1, power supply in a small PLC is often
Internal.
internal, it's inside. 2, PLC's control program is usually stored in
Hey.
non-volatile. So the control program is this, it's non-volatile. Nothing's gonna happen to this if I turn it off. Non-volatile, nothing's gonna happen. B. 3, a PLC processor cycle is called scan, where it goes through all the inputs. does the math, goes through all the outputs. 4, discrete input output module inputs and outputs are usually protected by isolation. 5, to generate its output signals, an analog output module uses a
DAC.
what's a DAC? Digital analog converter. Good. 6, RS-485 is an example of a serial network. Section 4, PLC programming. There's language is going to be important. There's different languages that this stuff is written in. My first highlight is 410, all 5 of those different languages: ladder diagram, function block diagram, sequential function chart, structured text, instruction list. This is how a PLC talks. Like this is this stuff right here. All right. So ladder diagram, that's in my experience has been the most common. Ladder diagram looks exactly like this. And they did that, like whenever they created PLCs, they did that because all the old school electricians that they had to teach how to do PLCs, if it looked the same on how they were hardwiring the contactors and stuff like that, they could program PLCs. So that is a language. A language is actually having like, it just gives you like, give me a normally open contact. And then what's the address to that contact? And I pull from a list of stuff that I put in my inputs of a light switch or whatever it is. And I put it on that contact, right? So they created that for old school electricians, but that's all I've ever used. That's mostly all I've ever seen or used is ladder diagram, LD. This is a dumb question this will be a question on the quiz and on the test. Out to the side, right, that there's 5 different languages, and their question has like, there's no LI language. Like write that. There's no LI. I don't know what LI stands for, but there's no LI language. It's kind of a goofy question. So I've done ladder diagram and function block diagram just a little bit. The function block diagram is it's almost like the code, instead of looking like that, it just has like a PID block that goes into like an output. And then like the code is like you click into this and it has like all the information inside of that whole closed loop circuit, like and then that's tied to like the output of something else. It's kind of written like that, but I didn't get into that too much. Like it was mostly this stuff. The other stuff is kind of like the code that you saw written on the computer. Like it's code like that. I never saw nothing that we had was ever written like that. But it's all a matter of like what you learned and stuff like that. The different languages that you can learn, probably the better you're going to be. 411 ladder diagram, first sentence is highlighted. Ladder LD programming, ladder diagram programming, also known as ladder logic, is the most widely used and oldest form of PLC programming. Function block diagram, 412, first sentence. Function block diagram programming is a lot like creating electrical schematic. I don't have anything in sequential function chart. Flipping the page at 22, structured text. First 2 sentences are highlighted. ST structured text is similar to many mainstream computer programming languages. ST programs resemble English. It can be understood to some degree just by reading them. Instruction list 415. First few sentences are highlighted like structured text and instruction list program. Like structured text, instruction list programming is text-based and done with a text editor. Unlike structured text, instruction list is essentially only readable to experienced programmers. Each program line is short, abbreviated instruction called a mnemonic. Most are just a few letters long and look like LD, ST, and JMP. Developmental tools, 416, top right of the page. First couple sentences up there are highlighted. Besides these basic tasks, some manufacturers also offer a PLC simulator that mimics basic functionality of PLC on a regular computer. Simulators can be used for program testing without the need for an actual PLC. That's like, we would run our stuff through a simulator quite a bit through, like at least the GE stuff, like you could run it through a simulator and like force stuff to come on and off and make sure the rest of the code worked before you downloaded it into the PLC. I highly recommend that if that's an option for you. It's making sure you don't have a virus in your code, by running it through a simulator. Ladder diagram programming 420. Relay, so this is like relay logic 421, going on to page 23, the first full paragraph, first sentence is highlighted. Outputs from a PLC's output module are shown as a coil on a ladder run. So PLC programming looks like this. Like the output looks like this. This is my coil, right? So that's like what would turn on my motor, my light, or whatever output function is attached to that. Same paragraph, right after where you see the capitalized false, we got a couple sentences after that highlighted. A latch coil is shown like a standard coil with the letter L in the center of the coil. When this rung is true, a latch coil will energize. When the unlatched coil, the coil with the letter U in the center with the same address is energized, the last coil will unlatch. So they have these down here. Like this is a standard coil. So this would work how I did it on the board, right? Whenever I push something, it would come on, and then if I let it go, it would turn off. Latch, if I have my start push button, I don't have to have my sealing circuit. So like that's taking care of that. I turn that on and it stays on until I hit my unlatch, right? And there's different advantages to that, like to making sure like stuff's not pushed at the same time. It's separating your code out. So it's going to look a little bit different than that. Like you would just have a start button on the latch, and then you would have the stop button on the unlatch part of that. So it's just a little bit different than how you would draw it on the hardwired circuit. But if you think about it more like my inputs going into like a computer, it makes more sense that when I push this button, this is going to latch and turn on. When I push this button, it's going to unlatch and turn off. If you think about it like that, rather than like when I push this, then power's going to flow through here and turn this on and turn this on, and now it's going to hold it on. Like in my mind, it's two different ways of thinking about it.
I'd like to join 3 separate lines.
Mm-hmm. Yeah, you can still make it work like this, but that's going to take more addresses. Like you're going to have to create this in the code rather than learn how to just learn how to make an input go to an output, and that's what happens. Rather than like sealing it in with the code that you create, you can it'll do it for you. And like if you're doing PLC code, you're not wiring stuff up anymore, right? You're gonna get used to doing code like this. It's just a little bit different way of how you're coding rather than how you're hardwiring. Timers and counters. So like you guys have all done, everybody done timers and counters? Y'all haven't made it there yet, but you're getting to the place where you're doing timers and counters. Obviously that's a hardware thing. I've already replaced one. Like people jack those timers up all the time, but that's because we're constantly switching and stuff like that. Most timers, like you set them and you leave them alone, but we're switching the knobs and stuff like that, and I have people jacking around. You can have a computer that has a timer in it. You don't have to have like a special module or anything like that. It just has a timer as a function of the computer. The whole second paragraph is highlighted. We got 3 questions coming out of this one paragraph. Of 422. The operations of software, timer, and counter are similar in that they're both counters. A timer counts the number of times that a fixed interval of time, such as 0.1 or 1.0 second, elapses up to a present value. For example, to count an interval of 3 seconds, a timer counts 3 1-second intervals. A counter simply counts the occurrences of an event. Both the timer and counter instructions require a register location in memory to store the elapsed count and another register to store the present value. The present value will determine the number of event occurrences or time intervals that are to be counted. It's just saying that you have options available to you to like, hey, turn this thing on for 10 seconds. And you're not having to like physically turn on an actual time. They go through a lot of the code and stuff like that, like how stuff happens. Like back in the digital logic circuit chapter, we talked about like how you put like an OR function next to an AND function next to an XOR function, and you can get it to like set and reset and stuff like that. And that's what the next page and stuff is going to go through, like especially the arithmetic. Like this is going to be like the data comparisons and stuff like that. I've got nothing on 24 and 25. Nothing in the arithmetic, but it's just like you're adding stuff up. Like this is how you get like you can have an HMI screen with like how many air compressors we build today, and like something's just ticking up. Like every time this proc switch goes off, then this number goes up. Like that's at the very basis, like what's a counter. Data comparison 424. This would be like the if then statements. Second paragraph in 424 on page 26, first sentence is highlighted. In the latter language, there are 3 basic data comparison instructions. You have equal to, greater than, and less than. So these are all things that you can use and say like, if this rail car weighs this amount, like if it's full, then you need to stop pumping and start pumping it into the next rail car. If they're equal, then they're both empty or something like that. Like that's where you can use this stuff. I'm just trying to think of like different instances, but it's all comparison stuff. You can think of filling any array of tanks or anything like that. If this one's full, then go to this one. If this and this are full, then go to this one. Like if then statements match with greater than or less than statements. Data transfer, nothing in program control. Like y'all can read through those sections, and it's all about moving at the very base that binary information from your devices into this and setting rules forth on how things talk to each other on a binary event, how to move stuff around from there to there to the program. But nothing highlighted there. 430 guidelines for programming and installation. Programming. 431, this is one of those dumb questions. First bullet point in 431, determine the task control out to the side, right first step. It's going to say like, what's the first step in like doing PLCs? It's going to be figuring out what you want to do. Like, what do you want this PLC to do? Do you want it to be a lift station and just turn on a pump whenever this is on? Well, this is good for you. Do you want to control thousands of things? Well, this is what you're going to need. Installation 432, first bullet point is highlighted. These are just all guidelines for installation. First bullet point, make sure the PLC has 25 to 50% extra capacity for future expansion. Even with these PLCs, don't load up this entire thing. Like get a whole nother rack. Don't load up these modules all the way. Like leave yourself space, because these modules can go bad, and you can transfer stuff to another one. But leave yourself extra space. That was never something I was a part of. Like I was just a part of, like, we had PLCs go bad. We had cards go bad.
So you tell me one of those cards is $5,000?
At least, yeah. Yeah, and we had, we would have like different lines had they would upgrade different lines at different times and upgrade the PLCs all at once with the VFDs. Like we had our GAL line, the line that like put the zinc coating on the steel, had old PLCs, and literally a card would go bad, and we didn't know how to fix it. We just knew what the cards would do. And like we had another line that upgraded. We just had boxes of these, except they were like this big. They were old stuff, and like, try this one, like slap it in there. And these all have like, if you have stuff like that, like you have to like the data transfer and stuff like that, like you have to tell what's talking to the processor by what slot in the back and stuff like that. But the wiring and stuff, you can leave wired up, like all your wires stay on this, and then like you put a new hard slot in, plug that in, and it's good to go. So it's actually pretty like, because whenever you do, like if you ever get to the place where stuff like that's happening, like you're telling your operators like we would do this stuff like once like a coil of steel started going, everything just kind of ran. And we were like, hey, we're gonna do a download in between passes, like in between when the last of the strip comes out. And they would like, you would get a roll of steel going, and like on nights, guys would like, all right, slow it down. You're gonna go sit down for like, you would run for like 45 minutes. So then we go pull one of these out, put a new one in, get that back on, download to the PLC. That's kind of always like a butt clenching moment. You're like, hope this works. And then like, if it doesn't, they'll put the old one back in and wait till they got the next coil up or something like that. But these can go bad. I never saw this, the Slick 5000. This is a new one. I never saw these go bad, but I definitely, in my experience, like there were older PLCs where cards were going bad. We just literally, we didn't buy new ones. We just had boxes, the old boxes from the line that they upgraded before. Make sure there's extra stuff. IO wiring. This is a highlight that I'm not gonna have a question for, but it's an extra question that can be on the test. It's one of the dumb ones, but fourth to last bullet point on page 29. Take precautions to avoid injury or damage when activating these input devices connected in series with the loads that are external to the PLC. Yeah, make sure when you're wiring up to these things that they're not on, because the PLC will turn something on. I'm not gonna have a question on that, on any of my quiz or anything like that. Just know that that can be a potential question. I've seen that question come up on previous tests. All right. On for 2 seconds. Wanted. All right.